So hello, everybody. My name's Andy Rivenes. I'm a product manager for database and memory. And we have today a special guest, Nigel Bayliss, who's the PM, the product manager for the Optimizer.
Hello.
So if you have questions, we do try to make this interactive. Please enter them in the Q&A rather than the chat, although I guess the chat might work. But the Q&A was easier for us to manage. And either myself or Nigel will try to cover those as we go through. As always, we have on the landing page, we have information about our office hours. We have our, we got Nigel's picture up there as one of our experts, but we have our previous office hours sessions. In fact, we did recently automatic in memory, and then we also talked about blockchain tables. But I like to always point out on our the other side of the screen, the resources that our blog, which I'll probably refer to, and then other information about database and memory. So you can always go there if you want to discover more about database and memory. And I should put actually a link there directly for our live lab. So if you'd like to actually try it out and try out some of the things we're going to talk about today, we'll do some demos. You can do that even in our live labs environment. So you can set that up. You don't have to have any licensing for the cloud, or you don't have to pay anything. You can just literally go to our live labs session, which is available on our blog if you want to get the URL, and run database and memory for yourself. So with that, I think we can dispense with that. And actually, I'll just bring it up since I have it there. There's our blog, and then our resources page. If you navigate to it, and we'll have that in the, this will be in the recording, but we have lots of information. And as I mentioned, the Live Labs link is right there if you want to click on it. So all you have to do is go to our resources page and connect there. So with that, we'll get rid of that. And we'll start. We'll do a little bit of slide just to kind of set the table for you. And then we're going to do some demos and show you how the optimizer costs, database and memory access versus index access. And then we'll poke a little bit under the covers to take a look at how the optimizer determines costing. But we're not going to get too far into that, other than if you're curious and you want to look at that. The motivation today was to make folks aware that database and memory runs, it doesn't use indexes, but it runs with indexes. And that's one of the reasons or ways that we can run mixed workload environments. And so that was kind of the point of today's session. And so my contact information's there, and you can follow Nigel on Twitter as well. So his Twitter handle is there if you want to see more. He also has, I didn't put the URL, I should have. He has the Optimizer blog that he writes articles fairly regularly about, and they get pretty in-depth about how the Optimizer works and statistics generation and how different features work within Oracle database and what the Optimizer is doing there. So also feel free to check that out. You can just Google for Optimizer blog and it will come right on up, and there's lots of articles there as well. Whoops. So with that, I almost forgot. And we also have an in-memory summit coming up. So on June 8th and 9th, we have our in-memory summit. I think we've been blasting on Twitter and LinkedIn. So if you're interested, it doesn't cost anything. You can go to that link, or you could send an email to Ranjan if you're curious about it, or if you want to join us. We'll be talking about database and memory, how it works, where we're going with it, and we'll have some folks talking about it that are what we call leaders, or basically Ahmed Al-Mari and Rich Niebek will be giving some keynotes, and then some customers will be talking about how they've used database and memory. So please think about checking that out. And with that, let's talk a little bit about database and memory in mixed workload. And that's really kind of what my focus was, or thought process in wanting to do this session, was really talking about how database and memory can work with mixed workload environments. I have kind of what I think is one of the key points about database and memory is the ability to run real-time analytics or write on the source data. Kind of the highlight at the bottom there is that the reason you don't have to change your applications to be able to take advantage of database and memory is the optimizer. And so that's kind of what the focus of today is. But really the idea that you can run database and memory and not have to only run it in a, say, a decision support system or a reporting system, or maybe in your warehouse, that you can really run it in a mixed workload environment right on your source data, which gives you the ability to glean all sorts of information about data in real time, as opposed to having to wait for that data to be transformed or transferred somewhere else before you can work with it. And so that's pretty important, I think, and one of the big benefits of database and memory. And then I'd like to point out, we have a demo out on our YouTube channel that talks about, we did this with the real world performance team, and it's about a 15-minute video, and I think I mentioned it before, but I like to point it out, that it actually shows a fairly busy, high volume OLTP workload, and then running analytic reporting with it. And so kind of the idea here is that to show basically that with database and memory enabled, we won't impact the throughput or the response time of those OLTP queries. With database and memory not enabled, it does impact it. And that's kind of what the point of the video and study was. And this just shows here, I got an enterprise manager screen, if any of you are familiar with enterprise manager. And the idea is that it shows, as long as you have CPU headroom, or capacity, I guess I should say, because database and memory is literally CPU and memory access. So as long as you have the capacity to run the workload from a CPU standpoint, then we won't impact your OLTP workload. Now, the other side of the hump here with the different colors in it is when database and memory is not enabled, well, those analytic reports are going to start doing I/O, and then things kind of start to fall apart. And so that's one of the ways or reasons that database and memory can really enhance a mixed workload environment and allow you to run a significant amount of analytic reporting without impacting your OLTP workload. And then something else to point out is that since those analytic reports will run much faster with database and memory, it actually, your overall capacity requirements tend to be lower. And so that can also provide you additional capacity headroom with database and memory. So anyways, that was kind of the lead in to the reason we're going to talk about all of this. And so feel free to our database and memory YouTube channel if you want to try to take a look at that. Again, it's a warning, it's about 15 minutes, and it goes into quite a bit of detail about how the tests were run and then the results. And so it's quite interesting, I think, but some background information for you if you're interested. And I keep trying to hit forward and I've clicked out. So what about indexes? Very quickly, typically we're not, so we've said in the past, and we still say it, that database and memory doesn't use analytic reporting indexes. So typically you can remove quite a few of those indexes. And along the way, we've gotten into the perception that you can just drop all of your indexes when you have database and memory. And of course, today's message is trying to convince you that no, that's not really what you want to think about doing. As a matter of fact, you can leave all of your indexes in place with database and memory, but since indexes do tend to require a considerable amount of space, workload to maintain, they generate undo and redo, and they're persistent, so they have to be backed up, that it can be advantageous to be able to get rid of indexes that aren't going to be used, because now you're using database and memory. And so that's really the removing index story, or removing the indexes story. But you're never going to want to get rid of your, at least due to database and memory, your constraint, your primary keys, foreign key definitions, typically your OLTP indexes that might be used for lookups. And that's kind of the story there. And so what we get into with some folks is the idea that, well, we're going to get rid of all of our indexes, and that tends to not work very well for your existing OLTP workload. And so the idea here is to talk about, well, how does this all work? How can I have indexes and database and memory running, and who or what arbitrates that? Because you don't say select from the row store or an index, or select from the column store. You just run your applications, because as we've said, you don't have to change your SQL. So what's going on under the covers, and that's kind of today's message. And this slide just shows the fact that as you have more and more indexes on your tables, OLTP transaction processing slows down, because it takes more and more effort to keep all of those indexes in sync. And so the ability to reduce the amount of indexes that you need, or analytic reporting indexes, can significantly speed up your not only your OLTP processing, but reduce your overall workload. I think that is that making sense, Nigel? But you're on mute. And that's what this story is about. With column store, I'm going to do that to you. I'm just going to try to draw you into the conversation.
Oh, okay.
So with the column store, those analytic reporting indexes can generally be replaced, but of course, we're not going to get rid of our OLTP indexes. Well, I just clicked on it and it went in. So let's talk about that. So
I guess actually, Andy, can I ask a question, Andy,
Absolutely.
quickly? When you say analytic indexes, you mean presumably these are indexes that are just created specifically for the analytic workload, is that correct?
Yes, definitely.
Yeah, right. Okay.
So, whoops. I keep clicking out of where I'm going, and I'm having trouble. I might have to go back to not full screen. Yeah, so these analytic reporting indexes are really strictly to be able to run reports in a reasonable fashion on row-based data. Yeah, right. So folks have, and to be honest, I say this fairly frequently, in mature applications, people will have as much data in indexes as they will table data, or more. Yeah. And so that takes quite a bit of overhead to maintain, again, the disk space issue and the backup and undo and redo. So that's really what we're focusing on, is analytic reporting indexes. These guys over here on the left, we don't touch those guys. They're needed for OLTP. And so we're not advocating getting rid of those, but as we'll see, database and memory does a table access in memory full, so it's not going to access those indexes. All right, so let's continue on, and that's what this slide's kind of showing, is that a traditional, and this is just a single table query, database and memory. We're going to see table access in memory full. We've talked about this in our Live Labs environment, or in our other AskTOM Office Hours sessions. We'll point out, we're going to jump to the demo in just a second, because we're just going to run some of these queries rather than do slides. But this is just kind of a little bit of background for you. Notice the rows on this data set. This is one of the ones I use for by example on my laptop, is 59 million rows. We're actually going, hopefully it will work, since we're having a little bit of VPN issue. I have another server within Oracle, and we're going to use quite a bit larger data set, which introduces some differences in cost calculations as well. So, and that should be hopefully fun and interesting. But the idea is that the reason the optimizer chose this path, this table access in memory full, was based on the cost. And so the cost here was 28,000, and the corresponding query, notice the no in memory hint. It's the same SQL statement, but with a no in memory hint. In the absence of any indexes, notice the cost is now 123,000. So I didn't have to hint, I had to hint them to not use in memory, because the optimizer said, oh, it's much less costly to access that data in the column store than it is in the row store. And that's kind of the theme for today. And then lastly, one of the things this is a demo that I do as part of my by example, is that not only is the choice to access that data through an index or maybe through the column store, but it can be a combination. And that's one of the things I think we haven't made as clear as perhaps we should have, is that it's perfectly fine for some access to occur through an index, versus some access occurring through the column store. In this case, we can even do a nested loop. So we talk about hash joins. It's possible to do a nested loop join with in-memory access and index access. And notice the cost again, $64.19. And obviously the date dimension table cost is very, very low, just 1. So most of the work's being done through the line order table, but that was, in this particular case, because the optimizer said, well, it's less expensive from a cost standpoint to access that data through an index than to do a table access in memory full. Now we're going to jump to the demo, and things are going to change a little. I discovered as I was experimenting, because this isn't fixed in stone in the sense that as we move through versions of Oracle, things change. The optimizer improves. Believe it or not, Nigel's doing his job there, improving the optimizer and his optimizer team, obviously. And so cost calculations, and then there become new ways for both within database memory, the optimizer in the database to access data. And so things will change, and that's one of the things I discovered in setting up some of these demos. And so let's, without any more ado, because I think I just had been talking about how the optimizer actually does cost things, which we'll come back to. I have, and hopefully, is that, can you see that okay, Nigel?
I can see that. Yeah,
okay,
that's
on
good.
The screen? Yeah, so I tried to make the font as large as possible.
Yeah, I can definitely read it. Yeah.
Okay, so I have I just didn't want my session to go away. So let's set this table here, set the stage a little bit, and I'm going to bring up, I have my cheat sheet. So let's see, I'll stick it over here for now. And so what I'll show you a little bit about what we've got set up. It's just our SSB schema that we've, whoops. Wow. It would help if I could type and pay attention to what I was doing. There we go. So we have our SSB schema. I've enabled everything for in-memory. We use this for most of our demos, and it will work just fine for us today. And I've populated this in the column store. And so I'll show you this very briefly, that we have space left in the column store. This is the overall view we've talked about in the past, where we can see this 1 meg and 64K pool. And then we'll take a look at, I can just type that one, what we have populated. So we have everything fully populated, bytes not populated is 0. We have all of our 5 tables in the column store. So that's kind of sets the table for some experiments. And so now what we'll do is we'll run that same query I had in the slide, but in this case, this data set is quite a bit larger. So it's 365 million rows rather than 59 million rows. So about 22 gigabytes is what that number right there is. So that's quite a bit larger than what I can run on my laptop, for instance. And so that query runs, and the point was to show what the execution plan looks like. So you notice that now we've done a full table scan, table access in memory full. We're looking for the max total order price, same query, but now our cost is a little bit higher, 29,000 is what the optimizer costed that, and it's doing a full scan. There's no filter predicate, so there's no possibility of doing an index access. And then I'm going to save everybody. I verified it. But it runs for over a minute. So what I got is just an explain plan somewhere here. Hopefully I put it in here. Maybe I didn't. Demo scripts. I thought I did. I did. Sorry, was looking at the wrong thing. So rather than enduring the running of this in the buffer cache, I'll just do a display. And yes, an explain plan isn't always accurate, but in this case, I verified. I could really run it for you if you really wanted to see it, but I don't think anybody wants to sit here and look at that. But with a no in memory, and we're just going to do a regular table access full against the line order table, the cost goes up considerably. So it's much more expensive to do table access in memory or table access full of the line order table than it is to do an in-memory access. So hence, without any hints, without having to tell the optimizer anything, it makes sense to do that in in-memory scan. And of course, that's the premise of how we can run without having to change your application SQL. But that's pretty simplistic stuff. So what I included, I realized I wanted to include some more complicated cases. So it turns out that even though we're doing an in-memory scan, I do have, okay, so the header's not there. I guess I could, that's all right. So on the line order table, I have 4 indexes set up. They're all visible, so the optimizer can use them if it wants. I did, as I set all this up, I did regenerate all the statistics, Nigel, so I think we're accurate on our statistics. We won't see any funny things. I didn't do anything with...
I'll be checking.
Yeah, there you go. With extended statistics or anything, but kind of one of the disadvantages of the star schema benchmark is it's very... there's almost no data skew in it. It's very randomized. So there's very little data skew, and I'll actually show that to you in a second. So the point of this was just that we have indexes available. So there are other access plans available to the database or to the optimizer if it chooses to use that based on cost. And that's kind of what we're going to look at. But based on that, let's look at something that will use an index. So all I have is a very simple query that's looking for one order key. And it turns out we have 7 rows. So this is actually the most skewed of the data is the 7-row cluster. Most of them are either unique or only 1 or 2 or 3 rows. There are a handful of order keys in the line order table that have as many as 7 rows associated with them. That's as far as data skew gets. So it's pretty, so we don't really have to worry too much about histograms or extended statistics or correlation because it's pretty much randomized. And that was not so much the point, but I'll just point that out. But notice that the optimizer now chose to access that data through an index because it's only getting 7 rows out of 365 million. The cost is very low to access that data through the index with a total cost of 5. There you go. Makes sense, right?
Right. Yeah. Yeah.
And so if this was an OLTP query, a lookup, maybe you're doing a lookup, maybe this is part of a larger transaction, it would make sense to access this data through an index. Even though in-memory is available and the line order table is fully populated and we haven't prevented the optimizer from choosing that. So what happens if we do that? What happens if we tell the optimizer, we want you to do a full table scan or in effect use the column store. So I put a full hint on there, which since the table's populated is going to cause a full table scan or table access. And since it's in memory, it's going to do a table access in memory full. And notice that we see a filter predicate and we're pushing, and we've talked about that in the past, that filter predicate into the scan. So we're going to do all this in memory. But look at the cost. Cost is still quite significant and way higher than the cost to access that data through the index. So that's why we had to hint it. And I know hints are bad and nobody should use hints, but for our purposes, we're using this to kind of illustrate the differences in cost. Now, one of the interesting things that I took a look at, and which I also will talk about in some of my other presentations, is if we look at the statistics, because that came back pretty fast, even though the cost was relatively high. And this is the session statistics associated with the query. And I didn't reconnect, but and actually, I'm going to do that just for fun so that we can get a clean set of statistics. So I'll rerun this. We'll rerun it like this because that way I don't have to worry about typing that. So that our session level statistics are all based just on the running of the query. And we've talked about this in the past, but just as a review, so the line order table looks like it has 680 IMCUs. So we're going to have to scan the columns. In this case, we're actually scanning order key, cust key, and revenue from the line order table, so 3 columns. And one of the key things to note is that we really only had to bring back 7 values, 7 rows, but we didn't get any pruning, which I thought was interesting, and that's the min-max pruning. But the bottom line is the column store, database in memory, can do things under the covers that we've talked about in the past to make this a little more optimal. So we're not doing as much work as we'd have to do to access this data without in memory, but it's still a lot more than we'd have to do with an index. And one of the interesting things that we'll talk about as we go through kind of what's going on under the covers with the optimizer costing is that, and I found that, and this Nigel will have a little issue with this, but the costing of the access isn't always discounted as much as it could be, because the optimizer just doesn't know how much work can be done under the covers. So there's cases where the in-memory scan will, even though the cost is, say, $32,000, it'll still run pretty darn fast because we'll get other optimizations going on that the optimizer won't always be able to take advantage of or understand. But it does factor a lot of that into the costing. So I'm just
that's a fair comment.
Sometimes we get some additional benefits.
Yeah, that's right. And in fact, it's interesting running this because if you sort of naively ran the 2 versions of the queries, the hint one and the index one, the run times are so fast that you kind of would think they're naively you'd think they're kind of equivalent, wouldn't you? But of course they are. That's very different because of the way that the operation.
Right. So if we were, say, we were going through hundreds of gigabytes of data, it would probably be, well, not probably be. It becomes much more magnified. You're right. Even my 22 gigs, it's still, especially in memory, it's just fast. Yeah. All right. So I had then what I added those 2 queries in because I thought it was I wanted to really point out the benefit of an index, and then now we're going to get to the original query that I thought would be most interesting, and so let's run this. So this is a little more complicated query, and I'm going to come back here. So now we're going to do a join, date dimension on the line order table. And it's a little more complicated in the sense that we have our join, and then we have a filter predicate on the discount amount, the quantity, and then we're going to just look at one day for a date. So there's some filter predicates in there. We've got a join, made a little bit more complicated. Now this query, in my previous by example queries, and I'll show you the example, but I had to hint it to get it to do it, would do that nested loop query. So it's actually, that query is the same one as the one I showed you here, maybe a little hard to see, that did that. It's actually the same query. But notice in this case, the cost is only $64.20, but there's way fewer rows. So it's a much smaller data set, which does affect things, which I discovered. Plus, I think we've done some work under the covers to optimize it, because lo and behold, what we actually get is a vector transformation on this query. So the optimizers decided that our cost is obviously higher, but our data set's much larger than what I just showed you. So now all of a sudden, running on my laptop versus running in a real environment, you start to see a little difference in the plans, because we're looking through a lot more data and having a cost accessing that data. We costed the same, but the cost itself is different. It's more expensive. So in this case, and I was actually really surprised when I ran this, I said, oh man, what's going on? And realistically, since the optimizer has, and we made in-memory aggregation more, we use it more aggressively than we have in the past. And we continue to do that because we get such good benefits from it. And we've talked about this. This query now is doing something called vector group by, which is enabled with database and memory. And we've talked about this. There's an AskTOM Office Hours session we can go back to, or you can go back to and review. But effectively, what the optimizer said was the least cost access to run that query is to do a vector group by. Even though there's only 2-table join, it's able to do that in a total cost of $33,980, and it ran pretty fast. I actually don't have timing set on, but we could see it runs fast. So I was actually kind of surprised because that's not something I expected. So what did I do? I said, well, let's see what the costs are if we hint this thing to tell it not to do that. So I've got another query. No vector transform, and I'm forcing it to use an index, which is going to create the basic same plan that I had previously. So the query ran very fast, and now we see that nested loops and accessing an index. But look what it did to the cost, which is why the optimizer didn't pick it in the first place. The cost now to access that and run this query is way higher, $246,000, as opposed to roughly $34,000. So the cost went way up compared to the vector transformation, and so that's why it was picked. And so this kind of just goes back to the idea that the optimizer is going to make its decisions based on cost, which means we don't have to change our application SQL, and whether we've created indexes or if we haven't created the right indexes, or we have things populated in memory, and that's kind of what Nigel makes his bread and butter on, and what all of his blog posts focus around is focusing on how to read an execution plan and understanding where costs are. But I found that very interesting because this is the plan I got on my smaller data set that I used for my by example, because this was an optimization we added in 12.2, I believe, to allow us to go ahead and not only use database in memory with hash joins, but also with nested loop joins, because we can actually scan the first table within memory and then probe the second table through the index.
Right. Yeah.
And Nigel may not have seen some of these things, so maybe you'll.
I haven't seen all of these, Andy. No.
Yeah. So let's say, the other way, the more traditional way to access this data, if we didn't have vector transformation available, which we do, but another example of accessing this data, same exact query, but this time I left the no vector transform hint in, but removed the index hint so that we get a more traditional database and memory query where we're using Bloom filter. So a hash join with a Bloom filter created on the date dimension table and then applied to the line order scan of the line order table. And notice the cost here is $34,059. So it's not that much different than if I go way back. Oops, did I go too far back? I think I went too far back. We go way back here.
Yeah.
But it is higher. So the vector transformation is saving us some additional work and basically making it slightly faster. Of course, as Nigel pointed out, in our case, the data set still isn't so large that we're talking hours or minutes. We're really talking seconds. But the point is, this is applicable no matter how large your data set is. So folks running terabytes or hundreds of gigabytes of data with their queries are the principle's the same. It's just what the optimizer can use to lower the cost and create the best execution plan.
And also, I guess it's about concurrency as well. So if you're running lots of these queries at once, then these little differences in cost, the cost you save then starts to multiply up, of course. So
yeah, definitely.
It becomes more and more important as you have more of these running concurrently, of course.
Yeah. Right. Yeah, definitely. And that's one of the advantages of database and memory is the ability, if we're running very, very quickly, we get in and out faster. So we, in theory, can run a larger volume of queries in the same amount of with the same amount of resources. So that's the idea of being able to actually, in some cases, reduce the capacity required to run a mixed workload environment. And of course, the index issue, because, for instance, in this query here, we don't need indexes. So potentially we could drop, probably not, depending on your workload, but potentially we could drop that index because we don't really need indexes on the line order table, unless, of course, we're doing on our first example, where we're just looking up, one particular order key somewhere back here.
Yeah, the sort of more OLTP
this guy right here.
style.
So then in that case, maybe we do really need that index. So we need to have the index for our OLTP, lookup type queries. But for larger queries where we're scanning and looking for, in this case, the sum of the revenue or the pricing with the discount rates and looking at the total revenue, more of an analytic type query, we're going to use database and memory. And I had one more query, which was, well, what if we didn't have in memory? So say we turned off in memory, we didn't have anything populated. What's this going to look like in a regular database that folks might not have in memory in? And so here we see that, okay, we can do our nested loop. Again, we're back to our nested loop access. We're going to, the date dimension table is so small that the cost is so small, we'll just full scan that. And now we'll access again our line order table by that index, because that's 246,000 is the least cost versus doing, if we had to do a full table scan here, it would be even higher cost. I guess I could have put that as an example as well, but I won't force the full table scan. We'll just suffice it and say the cost goes up considerably without database and memory being available, but that index is there, so it can use it. And so that was kind of the going through my demonstrations, and I don't want to take, we're actually, as I said, we try to keep it short, and I always wind up making these things long. Do we have any questions? I guess not. If we do, if you have questions, feel free to type them in to, I guess, either the Q&A or the chat. We're monitoring both. I think the Q&A is a little easier for us to manage. But if you do have questions about this or actually anything else, I had one more thing I wanted to cover. Since we've talked about costing and how this happens, the magic under the covers, the optimizer has this magical way of figuring out the costs. Well, it's not complete magic. There is actually a methodology. And
opening up the engine.
Yeah, the engine. So I was just going to cover that very briefly, because the optimizer does know something about in-memory. Now, as far as the row store, statistics and all the things that you've had to do in the past still apply. But with database in memory, the optimizer, and that's what this says, that you still have to deal with all of your row-based costs. But, and I'm going to skip this as well in the interest of time. But for the in-memory part, so the line order table, the date dimension table we've been looking at in the column store, the optimizer does look at the distribution of data and how it's created. And so the number of IMCUs, we mentioned it was 680 IMCUs. The questions are now they're coming in, the questions. So we'll tackle those in a second, unless you want to try, so SIMD. So we'll get those in a second, guys. Let me just point out that the optimizer does take into account the population and what's occurring to the data in the column store as part of its input to the costing mechanism. That's kind of what the point of that slide was. And that's what this slide also talks about. So it does have quite a few inputs to this. And actually all of this is visible. And I'm not gonna even bother with the slides I have with the trace file. So I'll just go show you one. And so I'm gonna leave that up there for our blog, and I'm gonna lower this guy down here for now. Don't forget where it is. And let's take a look. What I did is I actually created, so I'm gonna exit out of SQL Plus here. This will just take a second and we'll tackle the questions. That works. So it's possible to do an optimizer trace. We have on our resources page, and I'm sure Nigel has it on his blog as well. It's possible to trace what's going on with the optimizer and its decision to create the cost for, and focus isn't so much to analyze that as it is just to show you the inputs that the optimizer uses when tables are populated or objects are populated in memory. And so all I've done is I've set up a trace file identifier and made the max dump file unlimited so we get the trace file. This is really the secret sauce here to enable an optimizer trace. Obviously, the optimizer has to hard parse it to get that trace. In the interest of time, though, what I'm going to do is I'll just show you one. Yeah, this will be fine. We're just going to very quickly view it. If you've never seen one, might be of interest. If you've seen one, might be boring. But it starts out as a trace file. It's a background. It's written to the user dump desk, or the diag directory, if you will. And it has all sorts of information, which we're going to skip over. But what we're going to, and it tells you about all the setup, what's going on in the environment that the optimizer used. But the part we care about, we could have gotten this set up ahead of time, is we see the SQL query. But all I really wanted to focus us on was the statistics. So notice that we have here the statistics for the line order table. And specifically, not only do we now know the number of rows that are in the table and how many blocks that takes up. That's all the row-based information. Part we care about is this one right here. So notice that it knows that, and we verified this because I showed you the statistics, session stats when we accessed the query, the single line order table query. 680 IMCUs. It knows that there are, what was that? That's 365 million, sorry, 365 million rows in the table, and that's what's populated in the column store. So it does know the rows populated. It knows the blocks of that. Whoops. Other than the information for in memory, it also knows about the index information. And then with the other interesting part of this was cost calculation. So I'll just briefly show you that. But notice that since it's in memory, you'll actually see how the optimizer costed the access to the data, the IO access, where the accessing the IMCUs in the column store, and also the CPU cost to do that. So it basically costs both of those because it still has the basic framework of known memory, but it divides this up into both an IO cost and a CPU cost. And the interesting part, I think, not only from the IO cost, it factors in basically it looks for the most part to be a constant of the number of invalid rows that might be, kind of just uses a constant value from what I could tell. And then, and none of the actual calculations themselves are exposed. So you can figure out some of this information just like Jonathan Lewis does in the row-based stuff. There's some calculations that are pretty obvious. But then it also talks about, and this is what I had in the slide, the overhead, traversing the IMCUs, min-max evaluation has to do with in-memory storage indexes, the amount of pruning that it thinks it might get, the cost to stitch those the different columns we have. In this case, 3 columns we're looking at. Actually, in this one, I think this was I'm not sure which query I used, but in the case of the ones we were looking at where I have the 3 columns, knows it has to calculate a cost to stitch those columns back into a row to return back to the execution plan and then the calling SQL statement. So all of these things are factored in. And so really the point of this wasn't so much to show you the exact calculations, but just the inputs to it. And so you can go and look at this for yourself if you choose. By creating an optimizer trace on your own. And so that's kind of what those slides talked about. And we're actually doing okay for time. So we got a bunch of questions to answer. But that's kind of what I wanted to show today. And hopefully the message comes back that indexes aren't bad and that they work with database and memory to allow the optimizer to choose the least cost, the most effective access plan possible. Now, we understand the optimizer is not perfect. Sorry, Nigel. And I think you'd be the first to admit that. And so, but in general, for most queries, you're going to get the optimal plan based on cost. And this allows you then to run not only database in memory without having to change your application SQL, but also to run in any kind of environment, whether it's mixed workloads, you have OLTP and reporting together, or maybe you're in a warehouse where you're just doing large-scale analytic reporting, parallelizing, and accessing that data through pruning partitions, all that stuff, and all those access plans and magic the optimizer uses without database in memory, it leverages with database in memory as well. All right, I've done a bunch of talking. So let's see if we can tackle some of our questions.
Yep, we've got some questions.
So the first one is about SIMD. So kind of off the side of what we're talking about right now, but the person wants to know single instruction. So SIMD, or single instruction multiple data, is one of the ways that we speed up our scans by being able to do effectively array processing, in the sense that we can apply, for instance, filter predicates. We can do multiple rows or column values in a single, essentially, cycle, if you will, rather than having to do that one at a time when we're doing the scan. So that's what this is about. And the question is, can we use SIMD vector operations on Spark or Power processors? So database in memory is optimized. It has optimized libraries for Intel and Spark. On Power, there is not a specific library linked into database in memory, or Oracle database, sorry, to take advantage of specific SIMD instructions in the IBM Power processor. But there still may be SIMD benefits that are available when the database runs and makes OS level calls and runs on the chip itself. There is a way to tell the benefit of using SIMD processing, because it will show up in the session statistics. So I don't know if I can risk trying to navigate out of this, but if we go back and look at our query that we did, where I listed a bunch of the statistics, well, we'll just do it again. So I'll run this real quick. And we'll move on to questions. I'm probably going to take too much time answering some of these questions, and I don't want to miss out on folks' questions. But in this query, where I actually did, I ran the query, showed the execution plan. In here, see if any show up in here. It doesn't look like it. But what you'll see in here is SIMD information if we took advantage of SIMD processing here. And it doesn't, for some reason, it's not showing up in this one. I may have, it's possible I limited, here's the query I'm using, if you're interested. But I am %. So there are, oh, I'm sorry, staring at me right in my face. There you go. So this is a way to tell whether you took advantage of SIMD vector processing. So we show it up, it shows up in the session level statistics. I'm sorry, I missed that the first time when I was looking for it. So hopefully that answers that question. No, an academic question, Bloom filters. So why can a Bloom filter be used only for hash join of in-memory tables and not also for regular hash joins? Well, that's part of the advantage of database in memory. So when in-memory underscore size is enabled, Bloom filters are turned on. And the reason is because we're pushing that Bloom filter as a filter predicate into the scan of the data. And so Bloom filters actually get used in a bunch of different places in Oracle database. It's not just database in memory. And actually we'll use them with Exadata and table access storage full as well.
Yeah, that's it. It's like a package. You sort of deliver it to the service that uses the Bloom filter. So you've got that with Exadata scans, of course. Within memory.
And so I guess the reason is because the Bloom filter is being used during the scan as opposed to access that data through an index. Or if you think about it, if we're doing a table access full, we're actually having to return each row back and apply the filter predicate after the fact, as opposed to with database in memory, we can apply filter predicates during the scan, so we can actually do the join, the equality comparison right during the join, which is what gives us the advantage of not having to probe back into the hash table. Hopefully that
Yeah,
answers your question.
so it's really like a question of cost again. So, you use it under certain circumstances, the hash join, so the Bloom filter. So in theory, you could do it for any hash join, but because of the sort of trade-offs in costing, we generally do it when we're delivering the Bloom filter, say in parallel execution. And as Andy said, in Exadata and in memory, that's where we kind of deliver the Bloom filter bundle. So it's a question of the cost of using it. That's so we choose to use it where the cost is reduced rather than where it would add cost, if you like.
Right. So this is that example. So in this case, that join filter use is actually being applied as an additional filter predicate. You can see that right here, that function, during the scan itself, as opposed to trying to deal with it after the fact. So
I sort of think of it. Yeah, I sort of think of it being delivered to the thing doing the scanning. It's that kind of packaged and then delivered.
Exactly. Yeah, definitely. Are there any database and memory features that directly benefit queries and OLTP workloads instead of using traditional indexes? So the DBA answer is it depends. So the only time database and memory features directly benefit OLTP is when we're using database and memory. So the answer is only in the case where the cost of accessing the data in the column store is less than the cost of accessing in row store. Now, for instance, when we've talked about this in the past, vector group by doesn't, once in memory has been enabled, vector group by can kick in even if it's all row-based data, even if the column or the tables aren't populated in the column store. The issue there is that cost less than it would be to access data through an index. In general, I think it depends on the size of the data. But so the answer is yes, but really the way to think about this is database and memory, since it's all about scanning and filtering and aggregating with group by aggregations data, that it's really the idea is the data is the larger, if we're accessing larger amounts of that data, larger sets, that's where in memory is going to kick in. Again, if we're only looking for 7 rows, which was our very first example of accessing the data through an index, that's just going to be faster. So, and then we're definitely not going to do anything with DML, inserts, updates, and deletes. So you can certainly see in-memory access and plan usage in an OLTP or what I would call a mixed workload environment. But in general, database and memory isn't going to speed up OLTP processing because, one, we don't do inserts, updates, and deletes. That's all happens in the row store, reflected in the column store through metadata and then background repopulation. And for very small, like lookup type access, it's going to be less costly to access the data through an index than scanning the entire column or columns of the object, which we see in the cost calculations. Did I do okay there, Nigel?
Yep. Yeah, I think that's a reasonable answer. I mean, it's hard to imagine something that's different from that. But as you say, it always depends. There's always a little niche use case somewhere. But exactly. I think in general, that makes sense. Yeah.
So our database and memory features coming to your flagship autonomous database. So database and memory features are currently available in Autonomous Data Warehouse, the Flash version. So we support database and memory formats in DRAM, the column store, which we've been working with here. Also on Exadata, we support the database and memory formats on Flash. And Autonomous Data Warehouse takes advantage of that, the Flash version of the data for queries in that environment. It currently is not available in the other autonomous environments because you'd have to be able to do alter table, whatever the table name is, in memory, and you don't have that ability to do that. We are working on it. So the roadmap is that we want it to be available in the other autonomous flavors. Currently, though, it is available in ADW. Oh, and then we have one more Cindy question, it looks like. So a follow-up. I assume it means support Intel means x86 So AMD chips will also take advantage of SIMD in memory. Is that assumption correct? I don't think there are any current AMD specific libraries linked into Oracle database for SIMD support. That one I'd have to go double check on. I believe it's only Intel, and actually we've been spending some time looking at this recently for some customers. It's really just Intel and Spark have the specific libraries. In AMD, I'm not familiar with AMD support of SIMD. If you want to send me an email, because I have my email address, I could ask the development. But my understanding is no. But same with like the power chips, there still may be usage of SIMD outside of the specific libraries or operations that we've customized or created with database and memory for the Intel and Spark chips. But if you want to send me an email, I can verify that if you're interested. So, and with that, it looks like not only do we answer all of our questions, we're out of time. I can't believe we went through, that was an hour.
We are, I can't believe it, yeah.
That's the thing, it's kind of, I get rolling and we start looking at these demonstrations and time flies. I want to thank everybody for joining us. If there are any unanswered questions, and it looks like there's one in the chat. Comment like, there, sometimes it looks similar to zone maps to me.
I guess that's like, yeah.
Yeah, actually, and the funny thing is on Exadata, database and memory does recognize or work with zone maps. So we're able to actually leverage zone maps. So
yeah, they're similar principles, aren't they, where you can kind of skip. Yeah,
yes, definitely. Well, I want to thank everybody for attending. I know I want to be cognizant and respectful of your time. So we've managed to use up an hour. Hopefully that was useful. I want to thank Nigel. Thank you for attending.
Oh, thanks, Andy.
And imparting your wisdom with us.
A little bit.
And thank you very much for attending. We'll have, please check the AskTOM Office Hours page for our next session. I'm not sure what we'll tackle, but I'm sure it'll be a lot of fun. There will be a recording of this session. I will try to get it up in the next couple of days. And if you have any follow-on questions, feel free to ping me. I had my both my email address. You can follow us on Twitter. We have the Optimizer blog and the Database and Memory blog. Actually, that's kind of usually my last slide there. That's the URL if you want to try something out or get more information. And thank you very much. Thanks, Nigel.
Cheers, Andy. Cheers.